Welcome back to Further Solutions Academy. Welcome back to Further Solutions Academy. Further Solutions Academy. Encourage us more. Help us to share our videos. And also, if you have not subscribed before, help us to subscribe on it. If you have not subscribed before, help us to subscribe on it. Further Solutions Academy. In this platform, we have over 170 videos and within different topics. It means any topic you have problem, you have difficulty with, you can come here and learn without no problem. You will be fine at the end of the day. And any problem, any topics we are expecting it to be there, but it's not there yet, you can drop a comment below. Once again, Further Solutions Academy. Now, I'll be working on green theorem. We have been on a complex analysis, and we have been on how complex analysis is being formed. We have done the problem of complex number, what is complex number, and also the Movian's theorem. And we have done something on trig, hyperbolic, and trig function, hyperbolic function, and logarithm function of complex number. And also we have done two or more examples, like how do I handle it. Now this time around we'll be working on green theorem. Green theorem is just like we are talking about the limits, we are talking about integration, line integral, Now this time around, it means we are moving towards calculus part of a complex number complex analysis. Now on complex analysis, please take note of that. Now this time around, we are working on green theorem. It means this, I will call it green theorem just to know that we are still on complex analysis. Now when we talk about green theorem, it means we are talking about before we really understand this green theorem, please make sure you understand some things, like the first thing you need to understand, try to understand connection is very, very important to us. Now, which we'll be talking about multiplication, connection region. Please make sure go to your textbooks. All your textbooks, you are free to read them and understand what the textbook is saying. And also, you have to move on to also read on dwelling connected region. And also we need to understand the multiplication connected. Oh, sorry. These two. It means we're talking about something like this. We are talking about something like this is multiple connected region. Now we have something like this. We have something like this. It's being bounded with a depth. Now, but when we are talking about the second one, which is dual, I won't talk much on it. Connected region. It means if you are talking about you may have a contour that have a close, and it's being close. It's being like this. It's being like this. Now that is. It means there's a point that now it can be A. This can be B. This can be C. This can be C, and this can be A. This can be okay, B, C, and D, and so on and so forth. Now this one can be C1, C2, C3, C4, C5, C5, C6, C7, and so on and so forth. Now it means it's being connected, that is all about that. But you can read more of them, you will understand it better. Now, but this time around, I want to work on green theorem. I don't need to just quickly understand this contour stuff and get it right, and also you can be fine at the end of the day. Now, when I'm talking about contour, it means green theorem. Green theorem, if you have a closed curve, bounded by region, bounded by region R, and we have on that region, the first partial derivative of x comma y. Now, please, I've not done anything on partial derivation. Partial derivation, we are talking about, we have total derivation. I don't know how to explain that. This is total, this is partial. Please take note of that. This is total. Now, this is partial. Please take note of that. This is partial. And when we are talking about partial, it means when you are having 2x, y, x. Now, this is partial because of mixture of x and y. But total is just like 2x, the x. I think I will do one or two things on this. Maybe then that can come. This part of mathematics is complex part of mathematics. Means many things have to be done before. Now, when we talk about the green theorem, if you have a closed curve bounded by region R, and we have on the region the first partial derivative, which is this is partial, it means we are talking about x and y or the same function. Now, this is what we call partial derivation. It means my a of y of x, y, then integral of x, the x plus y, dy. Now, which can be equals to integral of r. This is the bound. It means partial of a of y with respect to x minus of a of x with respect to y with and total of partial of x, partial of y. Now, and also this. Now, that is what we are talking about. That is all we are talking about. Now, I think I need to prove this on this video. I may not be able to do fine, but not much on it. Now, if you are to prove it, you have to prove. Let me try to prove some things to you. Now, if you are to prove, you must consider the following. Now, the first thing you have to understand where we are coming from, which is the Hagan diagram. Now, in our Hagan diagram, we have a close now, this is a contour. Now, this is the what? This edge. This is B. Okay. And this is another edge. Now, this one can be F, this one can be E. Let me put E. Now, why here? This one can be A, and this one can be B. Now, let y equals to, which is a now, since we have it this way, we are now talking about curve A, B, D, and y equals to y2 of x, denoted by curve AFD. Now, let me just pick up. This is going to be F. This is going to be B. This is going to be okay. This is going to be D. Now, yes, that is what we are trying to. And here will be A. Here will be A. Now, it means I'm talking about integral and the region, which is the R of what? Partial of the partial of this y with of respect of x of this is going to be total, sorry, and of y. Please take note of that. Now, that's what I want to prove on this video. Please, I want to prove that this equals to this, that equals to that. Now, I need to, please take note of this information. They are very important. They are very, very important to our proving. Now, I will be using this and this and this. Please take note of that when you are writing. Now, okay, now let's try to do one or two work. I want to do this, and it means I want to prove this. I'm coming from here, integral of R partial of I of A y. Now, how do I go? I've showed that curve. It means on that curve, we'll be talking about what? The first one of what? A to B, which is A to B, on the one on this part. A to B, which is, I'll be having integral of, open a bracket of integral of, this one will be y equals to y2 of x, and y equals to y1 of x. Now, of this of y, of a of x, the x, the y. Now, since I have it this way, I can now continue by having, what can I do? Okay, now, I've set up my limits, and also, I will now move on by having, the first one is, I will differentiate this on its own. It means I will first go with respect of y. Now, once I go on respect of y, it means I'll be talking about integral of b of a, of b of a. Okay, from there, can I say that this function is of y, of 1. It means this, we are missing off, this is double integral for information, double integral. We're having x and y with respect of x and with respect of y. It means I will go for my y first. Now, it means I will go for my y to x, which by having integral of y equals to y1 of x and y equals to y2 of x. It means upper limit, upper limit and lower limit. of the function, which I'll be having partial of with respect of y and a of x of y and of x. Now it means I will handle the one of y first because of my function they are running on x. They are running on y. Since I will be running that first, it means once I integrate the first integral of it, it will be giving me integral of a to b, which is lower limit, upper limit. For this case, I'll be having a of x with function x1, y1, x1, y2. What am I using? I'm using something like this. We have done that earlier before. Now b and e, which is that Cartesian plane I drew before now. Now, since I have that, I'll be having of this, and I'll be having minus a of x, bracket of y and x of 1 of this, everything close with respect of what? X. Now, since I have it, I cannot continue by having, what can I do? I have this, I have this. I've told you in our integration videos that when we have integral of a b of f of x can be changed to minus integral of b a with f of x dx. Please take note of this function. It means what I'm having here, this can be changed. It means I can switch over something there because this lost O's. Now, by solving that, I can run through. Okay, this is 1. I can say that integral of okay b to a of x and x y2 of the x and minus integral of a to b and a of x y, which I'll be having 1 and 2 of the x. Now, by solving this, what can I do at this point? What can I do at this point? Now, I can now easily run towards the theorem I established there, that by solving up the stuff, you have something what you want to. It means I can say that minus integral of, now it will be turned upside down, which I'll be having okay, this one will be normal. It will be a of x and bracket of x1 the x minus integral of ba. Now ba, it will be a of x integral of s1 y2 dx. Now, since I have it that way, I cannot say that what can I do that it will be close. Now, it means I can bring out something like this, which is equals to, I have integral of ab of x of x1 y1 the x plus integral of ba a of x x1 y2 the x. Now, since I have it this way, what next? It means I can say that it means this is close. Minus of integral close, which is close, which is a of x and the x, which is equation 1, close curve. Close curve. It is a close curve. Now, I will now move on to the next one. How do I get The next one, it means I must run towards okay, pardon. Now, it means I must run towards integral of r, d of x, and a of y, and the x dy. Now, the first one, it was on respect of x. Now, I'm now on the respect of what? I'm now working on a function of what? This is function of x. Now, this one is a function of what? Of y. This is a function of y. Now, I'm done with function of x. I'm moving on to function of y. Now, which I can now say that this one can be equals to integral. This story have changed. Now, I'm looking at the limit of e to f. Now, before we are moving on the real axis, but this time around we are on imaginary axis, which means my imaginary axis, the lower limit is e, and the upper limit is what? Is f. It means with f of mine, I can run towards my integral of x1 y2, which is equals to. Now with this, now I can now say that now okay with this I'll be having this one will be function of y and function of now please, because we are moving on a real axis, I mean imaginary part of the Argand diagram of the Cartesian plane. That is why we're having e and f. Since we have it this way, it means we'll be talking about of this of respect of x, a of y, and d of x, d of y. Now, d of x, d of y. Now, this time around, this will be first. Now, please, we need this at this point. We need this. We need this. Very, very important. Now, since I have it this way, I can now continue by having integral of e to f, which I'll be having ay x 2y and minus ay x1 y, and which I'll be having which I'll be having with respect of dy, which is now with respect of y. Okay, now since I have it this way, I can say that integral of f e and a of y x2 y of dy minus integral of e f and a of y x and of dy. Now, since I have it this way, I can do the same thing, which is what I hold this time. I can say that my integral of e of f a of y x2 y1 dy minus integral of f e a of y x1 of dy. Now, what am I trying to? Minus times minus, it's always equals to plus. Now, minus times minus always equals to plus. Since I have it this way, it means I can say that what next? I can say that integral of e of f is of ay x2 y of dy plus integral of okay, it will be integral of f e a of x1 y1 y. Now, which it will give us this, and this it will be integral of close of ay dy, which is equation 2. Now, add equation 1 and add 1 and 2. This is my 1, this is my 2. It means once I add it up, I'll be having integral close of a of x dx plus a of y dy, which it will be equals to integral of r of a of x all over respect of x plus minus of a of y with respect of y close with respect of x and respect of y. That is all. That is all. That is all. Now, that is all on green theorem. Now, with this, we have proved our green theorem that this is equals to this. In our next video, we are to work on example to illustrate the green theorem. Once again, this is Further Solutions Academy. Further Solutions Academy. Encourage us more, help us to share our video and also subscribe to our channel. Help us to share and subscribe. We have over 180 videos on this channel. It means we can learn on this platform without no problem. Once again, thank you for watching.